All right, so we're looking at this picture where the limit as x approaches c does not exist. But here's what we can say. The limit as x approaches c from the left of f of x is L1. The limit as x approaches c from the right of f of x is L2. So when we say the limit as x approaches c, and we don't say left or right, that means both left and right. So the limit as x approaches c of f of x does not exist. But f of c equals L1 because that's where the hole is filled in this picture. By the way, you could have either of the holes open, or you could have both of them open. So you could have the top one full and the bottom one open. You have the bottom one closed and the top one open. You could have both the top and bottom one open, but you cannot have both the top and bottom closed. Why not? Why could you not have both the top and the bottom closed? Because then f would not be a function. And in calculus, we only talk about functions. So if you had both the top and the bottom closed, you would have an x that has two different y values, would not be a function. All right, so what you need to be able to do is look at this picture and determine these four things. But I'm going to keep sort of peeking behind the curtain and say, what does this really mean in terms of our definition of a limit? Now, this document that I have here is called Definitions of Limits. It's on the website. It's on the Google Classroom. You can pull it down and look at it, but you don't have to learn any of it, but it's a good idea to look at it. So here's our limit as x approaches c, and here's our limit as x approaches c from the right. So if we say x is approaching c from the right, all we're saying is that the x's are always bigger than c. So if the x's are always bigger than c, all we have to do is drop the absolute value in x minus c and say x minus c is a positive number. That forces x to be greater than c. And then everything else goes the same way. So likewise, when we do limit from the left, our x's are always going to be less than c. So then we just say, and we still drop the absolute value, but we turn it around, c minus x. So for limit as x approaches c from the left, for every epsilon, there exists a delta. 0 is less than c minus x is less than delta. So by saying c minus x is positive, we're saying that c has to be larger than x has to be less than c. And everything else goes the same way. So what happens now is when you go to look at your epsilon band, let's just look at limit as x approaches c from the left. We go to look at your epsilon band. So what this statement does by saying it's not an absolute value anymore means we're only going to look at a delta band that does not include c, but does include the left of c, but not the right of c. So your delta band is only over here and not over here. So mathematically, changing from this absolute value to this without an absolute value cuts off one side of the delta band. And then, yeah, for every x within that half delta band, your f of x values fall within the epsilon. And if you take a smaller epsilon band, you can take a smaller delta band. That all still works. Okay, so the fundamental difference, by taking off the absolute value, we get either just the right-hand side of the delta band or the left-hand side of the delta band. That's what's mathematically going on behind that. But all you have to be able to do is look at situations like this and interpret them. So if you saw, just to give it some specific numbers, if you see a graph, and let's say you see this, and ba-ding, and let's say this is 2, and this is 5, and this is 3. All right, so what you have to be able to say is, what is, let's put 4 over here as well. What is the limit as x approaches 3 from the left of f of x? What is the limit as x approaches 3 from the right of f of x? What is the limit as x approaches 3 of f of x? And what is f of 3? So those three questions all revolve around the x being 3. So they're only talking about what's going on here. All right, so take a minute to answer those. Okay, so hopefully you paused and answered those to the best of your ability. So the limit as x approaches 3 from the left, we're coming from the left, the y values are approaching 2. It's 2. The limit as x approaches 3 from the right, as the x values approach 3 from the right, the y values are approaching 5, so that's 5. The limit as x approaches 3 of f of x, since it's different from the left and right, that does not exist. And by the way, you're going to start writing this, DNE, for does not exist. Everyone in the AP Calc world is going to know what that means. You can write that on your AP exam. It means does not exist. I should put that on the abbreviation list, but I haven't done it. Okay, and then what is f of 3? So f of 3 is not where the hole is. If these were both holes, we would say f of 3 also does not exist. But now f of 3, it's where the point is 5. All right? Okay, so now let's look at 4. Can you say what is limit as x approaches 4 from the left? What is the limit as x approaches 4 from the right? What is the limit as x approaches 4? And what is f of 4? All right. Well, and we're going to assume that that looks like it's also at 5, right? So let's say this is the point 4, 5, and it's also on the graph. There's a little peak in between, but it doesn't matter. All right, take a minute and see if you can answer these. Okay, your minute's up. Limit as x approaches 4 from the left. As we approach 4 from the left, our y values are approaching 5. As we approach 4, as the x's approach 4 from the right, the y values are again approaching 5. Since the limits from the left and right are the same, as we approach 4 from either direction, that limit is 5. Now, it also happens that f of 4 is 5. So a very special magical thing happens when all the limits and the function value are the same. We're going to get to more of this later. We're going to say f is continuous at x equals 4. But f is not continuous at x equals 3. Okay, so more about this later.